Isotopes produces the largest amount of energy compared to all other conceivable reactions between light atomic nuclei. The deuterium-tritium reaction takes place according to the following principle. The two atomic nuclei fuse to form a helium nucleus, and additionally, they set free a neutron. This causes a large amount of energy to be.
The Sun and Earth both emit electromagnetic radiation. This movie will help you describe the differences between the types of radiation emitted by the Sun and the Earth. Electromagnetic radiation is energy that travels in the form of electromagnetic waves. Different types of electromagnetic waves carry different amounts of energy. The shorter the wavelength, the more energy carried by the wave. The wavelength of emitted radiation is determined by the temperature of the object it comes from. The higher the temperature, the shorter the wavelength of emitted radiation. The Sun, with its high surface temperature, emits a great deal of high-energy, short wavelength radiation. Energy emitted by the Sun is also referred to as solar or shortwave radiation. Most of solar radiation is the visible light we see with our eyes, but it also includes wavelengths that we cannot see, like the ultraviolet light that causes sunburn. The Earth, however, being much cooler than the Sun, emits lower energy, longer wavelength radiation. Energy emitted by the Earth is also referred to as terrestrial, which means land-based, or long-wave radiation. Although we cannot see long-wave radiation with our eyes, we detect it as heat. In summary, the types of radiation emitted by the Sun and the Earth are determined by their temperatures. The Sun, which is very hot, emits high-energy, short-wave radiation, while the Earth, which is much cooler, emits lower-energy, long-wave radiation.
Thermal energy moves around us all the time. You might walk outside, you might feel the rays of the sun hitting you. That's one way that energy moves around. You might put your hand on something that's a little bit too hot and get burned by it. That's another way thermal energy moves around. Or you might jump into a lake and notice that some parts of the lake, like below the surface of the water, are nice and cool, and the surface is kind of warm. And so, why does that happen? How does thermal energy move around? Well, that's what this video is all about. How does thermal energy move? First off, thermal energy only moves one direction, and that is from hot to cold. It's very important that you note that thermal energy only goes from hot to cold. And that comes down to where heat comes from. I mean, heat, when we're talking about temperature and thermal energy, the reason things have thermal energy is because the particles are moving really quickly. So imagine a bunch of vibrating particles that have lots of energy. They're bouncing all over the place. And then imagine some cold particles that aren't really moving very much at all. They're just kind of vibrating slowly in place. If you put those hot particles, the ones that are bouncing all over the place, next to the ones that are kind of slow and cold and not moving very much, are the cold ones ever going to give energy to the hot ones? No, that just wouldn't make sense. The high energy particles are the ones that are going to transfer energy to the cold ones. And that's what always happens. It's just the natural flow of energy is always from hot to cold, or from high energy to more low energy. And so when you look at these pictures here, this glass of ice water, you might think that the ice is actually cooling down the water. Well, it is, all right, it's cooling it down. But what's really happening scientifically is that the energy from the water is going into the ice cubes, and that's what causes them to melt. It's not the ice cubes transferring their coldness to anything. It's really the ice cubes are sort of sucking the thermal energy out of the water. That's why it gets colder. And the same thing happens outside. Found this cute picture of a baby all bundled up. We bundle up in the winter so that we can keep our thermal energy, so that it doesn't get sucked out by the cold. See, the high energy particles in our body are bouncing all over the place.
Remember that white light from the sun is made up of all the wavelengths of colors in the visible spectrum. When we point the probe at the sun, the spectrophotometer shows full intensity of all wavelengths in the visible spectrum. You may also expect a white light bulb to emit all the colors in the visible spectrum. However, when we use the spectrophotometer, it shows that some wavelengths are not emitted as much as others. Here is that red ornament under sunlight. Now it is easier to see that the ornament does reflect red wavelengths of light. Compare how the ornament's reflected light is different under the white light bulb than when it is under the sun. This illustrates how the properties of light are not always consistent with what we see. Another example is when we mix colors of light on the surface of a table. The combined emissions from a green bulb and a red bulb look yellow. However, the probe does not show that yellow wavelengths of light are present. So why do we see yellow? You are probably familiar with how paint combines to form additional colors. The primary colors of red, yellow, and blue can be combined to create other colors, such as orange, green, and purple. This is called a subtractive model. However, when we mix light, it follows an additive model. The additive model is also called the RGB model because when we combine the primary light colors of red, green, and blue, it produces additional colors such as magenta, cyan, and yellow. We can use the RGB model to explain why combining red and green light appears yellow. You also investigated how light is transmitted through colored water. The spectrophotometer shines white light through the cuvette and measures the absorbance and transmission of the light when it passes through the liquid. You probably expected the yellow wavelengths to be transmitted, but with your knowledge of the RGB model, you should also understand why green and red wavelengths are also transmitted. What wavelengths are absorbed by the yellow water? Transmittance and absorbance have an inverse or opposite relationship. So the wavelengths that are absorbed are those that are not transmitted. In this case, blue and violet are absorbed.
Thermal conductors and insulators are used to control the flow of thermal energy. When you're out on a cold day, you want to control the flow of thermal energy and keep it from leaving your body. That's why you wear a jacket. In this video, we'll define what thermal conductors and thermal insulators are, and we'll look at numerous examples of them so you can identify them on your own, use them in your projects, and use them in real life.